Before we can get to the algorithm, we have to consider another abstract concept, the NFA. We'll take a look at the NFAs now. First of all, there's a duality, well-known duality between regular expressions and DFAs. DFA is a discrete finite automaton. That's an abstract machine from theoretical computer science, which is a very simple idea. It's a state machine for recognizing whether a given string is in a given set. And if you're not familiar with those, they're very easy to understand, and we'll look at some examples. In a little summary from basic theoretical computer science, there's a very important theorem called Kleene theorem that was developed actually here at Princeton in the 30s. And it says that for any discrete finite state automaton, there exists a regular expression that describes the same set of strings. And equivalently, for any regular expression, there's a DFA that recognizes the same set of strings. And this is just an example. And if you have seen this, this sort of thing will be familiar. And if you haven't, you will understand better as we get into it. So a discrete finite state machine is a machine that has states that are labeled, and it has transitions from state to state that are labeled with characters. And the way that it works is, if it's in a state and it reads, for every state, it's well defined. If the next character is 0 or 1, there's another state to go to. So for example, at state 0, if you see a 0, you stay in state 0. If you see a 1, you go to state 1. In state 1, if you see a 0, you stay in state 1. If you see a 1, you go to state 2, and so forth. So at every state, read a character and go to the well-defined next state. That's a discrete, a deterministic finite state automaton. And so that's a machine. You start it up on a string, and it reads all the characters in the string. And then if it ends up in a state that's a so-called terminal state, started on the start state. Terminal state is just indicated by this exit arrow in this example. Ends up in the right state, you say that it recognizes a set of strings. And so that's a way to determine if a given string is in a specified set. The machine specifies the set. In an RE, we specify the set by writing characters in stars and meta characters in parentheses. And this regular expression recognizes the same set of strings, describes the same set of strings that's recognized by this DFA. Kleine's theorem showed that it's always possible to construct such a machine. So that gives a basic plan for developing pattern matching implementation. And this is developed by Ken Thompson at Bell Labs, one of the developers of Unix, and this facility was an important part of early Unix. Developed this idea based on the well-known theorem from theoretical computer science, is let's try to build a machine the same way as we did for Knuth-Morris-Pratt, where we have no backup in the text input stream. So we just got a finite state machine, but Knuth-Morris-Pratt, we built a machine for recognizing the one string. How about building one for multiple strings? And that would give us a linear time guarantee. So the underlying abstraction is a deterministic FSA or DFA. And the basic plan is to just go ahead and take your pattern that describes a set of strings and use that to build a DFA, and then simulate the DFA with the text as input, same way we did for Knuth-Morris-Pratt. And if it accepts, we say we have a match. If it rejects, we don't have a match. This is a fine plan, but it's got a flaw. The bad news is that the plan is infeasible because the number of states in the DFA might be exponential in the length of the RE. So it's got too many states. The proof of Kleine's theorem, the standard proof of Kleine's theorem, involves an exponential number of states. And it's not that difficult of a proof. If you're interested, be sure to look it up. But for practical standpoint, too many states, can't use that as the basis for our algorithm. but there's an easy revision. And again, this gets back, it'll give us a quadratic time guarantee, and actually in real life it's usually linear. And all we do is change the abstraction to use a non-deterministic finite state machine, an NFA, rather than a DFA. So in the same basic plan, we're going to build an NFA. It's a different kind of machine, but actually it's also the case that for any regular expression we can build an NFA. And vice versa, Kleeni's theorem can extend to this. And so we're going to simulate the NFA with the text as input. And so what do we mean by non-deterministic finite state machine? That's what we have to talk about next. And we'll just do it with this example that we'll use throughout this lecture. It's very similar to the DFA that we had before. Now we're going to put the characters in the states. And actually, the kind of NFA that we're going to build, we're going to have one state for every character in the regular expression. So this is an NFA corresponding to this regular expression. We always enclose the regular expressions in parentheses just to make everything work. And then got this regular expression here, A star B or AC D. Then we're going to show how to build this NFA and then simulate it to recognize the regular expression. And how is it different than a DFA? So there's a character in every state, and if the character is a text character, it's the same as before. We read that text character and move to the next state. But it's more general kind of machine because states also have what's called epsilon transitions. And with an epsilon transition, the machine is allowed to change the state without scanning any text. So at the beginning, the machine can go from 0 to 1 to 2, back to 1, 2 to 3, back to 2, or it could go from 0 to 1 over to 6. There's lots of places the machine could go without scanning any text character. But we do have the black match transitions that scan text characters. And so those are the rules the machine operates by. And the final rule is, when does it accept, when does it decide a string is in the pattern? It accepts if there's any sequence of transitions that scans all the text characters and ends in the accept case. It's a way of specifying an infinite set of strings, but it's got this non-determinism. It's not always determined what the machine will do next. It's a little bit of a mind-blowing concept in theoretical computer science, but this particular example actually shows how such a concept can be made concrete and actually give us a widely useful algorithm. One way to think of a non-deterministic machine is a machine that has superpowers and can guess the proper sequence of state transitions to get to the end, get to the accept state. Another way to think of it is the sequence is if you provide a particular sequence, that's a proof that the machine accepts the text. And so this isn't a real machine. We don't have real machines that can guess the right answer, but it's a completely well-specified abstract machine, and we can write a program to simulate its operation, and that's what we're going to do. So let's just make sure that everyone's got the concept down. So say we have the question, is 4A's followed by BD, is that accepted by this NFA down here? And the answer is yes, because there is a sequence of legal transitions that ends up in state 11. So in this case, we'll take an epsilon transition from 0 to 1 to 2. And then we've got 4A's, so we'll chew up 4A's. 1, and then go back. 2, and then go back. 3, and then go back. 4, and then we'll be in state 3. And then at that point, we'll decide to take this epsilon transition. We'll assume the machine decides to take this one. Then it recognizes the B. and moves to state 5. And then at state 5, it no place to go but to state 8, and then takes the epsilon transition to state 9 and recognizes the D. That takes it out to 10 and 11. So there is a sequence of state transitions that get to 11 and recognizes all the characters in the string, so therefore it's matched. What about, so it's true that there's sequences that the machine might guess and go the wrong state or stall. It doesn't matter as long as there's some sequence, and we're going to assume that the machine always guesses the right one. So for example, if the machine just recognized 3 A's, 1, 2, 3, and then went to state 4, it would get stuck because there's no way for it to get out of state 4, because at state 4 it's looking for a B and it's sitting on an A and so forth. So there's definitely things that the machine could do that'd be wrong, but we don't care as long as there's some way for it to get through. And then what about if it's a string that's not in the language recognized by the machine? Well, so we have to argue about all possible sequences and prove that no sequence of legal transitions ends in state 11. And that seems to be a fairly complicated sort of argument. So in this case, the machine could recognize a bunch of A's and then go to state 4, but again, there's no B, so there's no way it's going to get out of state 4. And so you can make a general argument like looking at the machine, any string that it recognizes has to end in D, and this one doesn't end in D. But that's a much more complicated thing than we're talking about, is to try to come up with a simple machine that'll decide whether or not a string is in the language that it specifies. So the question that we have is, we have this non-deterministic machine. How are we going to decide whether a given string is in the language that it recognizes? So for deterministic machines, like we use for Knuth-Morris-Pratt, it's very easy because at every time there's only one possible transition. But for non-deterministic, if you're in some states, there's multiple ways to go, and you have to figure out the right transition. But actually, the situation isn't so bad. What we can do is, to simulate the NFA, is just make sure that we consider all possible transition sequences. And that's what our algorithm for regular expression pattern matching is going to be based on. That's what we'll look at next.